So here's part B of problem number 2 from the 2013 BC exam. We've got these polar graphs. In part A, we found the area between the polar graphs that's shaded right here. In part B, what they want us to do is they want us to assume that a particle is moving along the polar graph that's defined by the polar curve that's defined by this limacone here, so defined by this equation. And what we're told is that at time t seconds, theta is equivalent to t squared. We want to find the time t in the interval from 1 to 2 when the x-coordinate of the particle's position is -1. So this is kind of tricky here. We want to know when the x-coordinate of the particle's position is -1. First thing I want to focus on is this. If we're on this graph and we're looking for an x-coordinate, what we need to remember is how to relate a point in the coordinate plane with a point in the polar plane. They're both two-dimensional planes, and so we should be able to relate the two, and it's pretty simple to do so. If we just call this point arbitrarily x comma y, the x value is this distance across the x-axis and the y value is this distance up there. So I'm going to call this x and I'm going to call this y. But if we're in the polar plane, our radius would be out to a circle and then around the circle. So our radius would actually be here, and the angle that we've traveled around that circle is specified by that central angle theta. And so if we went ahead and tried to develop a relationship between x, r, and theta, it's pretty simple to do, and there's a formula that you've probably memorized, which we're basically doing a little derivation of right here. And that would be that the side labeled x is adjacent to the angle theta, and the side measuring r units is the hypotenuse of the right triangle. And so the relationship between adjacent and hypotenuse would be the cosine ratio, and it'd be cosine of the angle theta. That's going to be equivalent to x over r. And so what does the x-coordinate equal? Well, the x-coordinate is going to equal r times cosine of theta. Now, if we're on this graph, we know what to put in place of r. So the x-coordinate at any value theta on the limacone is going to be found by taking 4 minus 2 sine of theta times cosine of theta. So I just replaced r from the relationship we just developed with what we know r to be equal to on the graph that we're to be concerned with. So let's try to figure out what this means now. So particle moves along the polar curve, r equals 4 minus 2 sine of theta, so that at time t seconds, theta is equivalent to t squared. Theta is equivalent to t squared. Find the time t between 1 and 2 when the x-coordinate of the particle's position is -1. Well, I think what we can do, based on what we have written out right here, we can find the theta value. Theta equals what when x equals -1? So let's start by finding that theta value, and then we should be able to use this relationship between theta and t in order to find the corresponding t value. Now this is a calculator problem, and I'm definitely going to use the calculator to my advantage in order to solve this equation. So what I'm going to do is I'm going to actually graph two things on the calculator, and then we'll restart the video in just a second. So now that I'm all caught up to where I need to be, I kind of misspoke when I paused the video a second ago. If this is the relationship between x and theta, I want to know when x equals -1. So what I'm actually going to solve is I'm going to put -1 in place of this x here. So the equation that I'm going to solve graphically is actually going to be this one. And so this is a little bit goofy because I'm not graphing in polar mode. If you're going to solve an equation graphically, you're still going to have to graph in function mode and solve using either intersect or zero, the same way that you have from the function mode graph screen. So I'm going to graph two things. I'm going to graph this, but the weird thing here is that I have to replace the variable theta with x's. So I've typed in the right side of this equation for y1, and I've got y equals -1 in as the other equation. I want to know when these two things equal each other, so I want to know when these two graphs equal each other. So if I graph these, you see that we should be expecting a value between 1 and 2 when it's all said and done. Now I'm going to find a couple intersections here. So I see an intersection here I'm just going to use the calculator's capability to find that. So the intersect feature from out of the graph screen, I'm just going to kind of bounce over toward this intersection. There's my first curve, there's my second curve, there's my guess. So I get the x value of about 2.30, 2.039125. I'm going to take all the accuracy that the calculator provides me with right there. I'm only going to try to round this off once toward the end if I can help it, even though this is already truncated by the calculator a little bit. I'm going to find one more intersection just in case here. So if I go for one more intersection, the intersection is to the right of these. So first curve, second curve, guess, yep, that's good. So the other intersection I see, and I guess I'm kind of using bad notation as I jot this down on my screen here, because although the calculator is telling me that these are x values from the graph, they're really values of theta. So I'm just going to go ahead and fix that up a little bit. So these are the theta values when the x value on this polar graph, the limacone, not the circle, the limacone would be equal to -1. So I guess that would be, you know, the theta value that we see about right here, and the theta value that we see down here. Right here would be on the graph where x is -1. So we get two values. Now we want the value that has t ending up between 1 and 2. Now these are values of theta that we have down here. There's this relationship between theta and t. Theta is equal to t squared. So if we want to figure out for what value of t, when t sits between 1 and 2, is the position of the object going to be -1 for its x-coordinate? All we have to do is take these theta values and say that they're equal. I'm not going to repeat everything here, but we say that this is equal to t squared, and then we're going to take the square root of each side to figure out what our value of t is. So the reason why I found two values here is because it was kind of weird that neither of these values was between 1 and 2, and that's because that's the interval for t, not the interval for theta. I believe if we take the square root of this one, we are going to get an answer between 1 and 2. If we take the square root of this one, since that's above 4, we should get an answer that's a little bit above 2. So I got this a minute ago just in case, but we're not going to need it. Our result for t is going to be t equals square root of 2.03. And we'll just go ahead and wrap this up with the calculator once again here, which seemed to disappear on me. Let me get that back. So I want to take the square root of, this is stuff left over from earlier, square root of, I'm not just going to type in square root of 2.03. I'm going to type all of the digits of accuracy that I took from the graph screen a minute or two ago. So 2.039125. And the value of t where this happens is approximately 1.42. I could write that as 1.427 if I want to round it to 1.428. As long as I take 3 digits of accuracy, truncated or rounded, I'm good to go. So I think that's all we needed to do for part B, right? Find the time t in the interval 1 to 2 for which the x-coordinate of the particle's position is -1. Yep, we did that.